Can you see the slide on the problem, reactor performance for design charts or from design charts?
Yes, miss.
So we'll just read again the problem. I'm sure some of you already took a screenshot of this. Then I'll share to you the Jamboard where the solution was written and then discuss everything concerning this particular problem. So we're given here the aqueous reaction of 1 mole of A reacting with 1 mole of B, forming the products with known kinetics, which is second order. You have 500 times the concentration of C sub A times C sub B as the rate law. Now this is to take place in an experimental tubular reactor, which is to be assumed as the plug flow reactor under the following conditions. So the volume is 0.1 liter. The volumetric feed rate is 0.05 liter per minute. And the initial concentrations of A and B that's fed to the reactor is at 0.01 mole per liter. Now, these are the required informations. So we are to determine the fractional conversion of reactants that can be expected. Now, if we're going to use if we're going to have the same conversion, but we're going to use a different reactor, this time a stirred tank reactor, what degree of, or rather what size of the stirred tank reactor will accomplish the same degree of conversion? And then let us see what conversion can be expected in a mixed reactor equal in size to the plug flow. Okay, so let me share to you the Jamboard where our solution was done last meeting. Okay, wait class. Okay, so this is the Jamboard. Can you see the Jamboard where the solution to the problem was written? Can you view it in your end?
Yes, miss.
Now, since we're given an aqueous solution, so there won't be any changes in the volume. So it's a constant density system, and the fractional change in the volume will be 0. Then you have a PFR. So you are given a plug flow reactor. And then this is your stoichiometric equation, A plus B, forming the products. And this is the volume of the plug flow reactor, the volumetric flow rate, the initial concentrations of A and B, and this is the rate law. Now, the required information are as follows. So you are to determine the fractional change in the conversion in the PFR, in the original reactor. And letter B, you are to determine the volume of the mixed flow reactor that will accomplish the same degree of conversion in the PFR. Now, letter C asked if your volume for the mixed flow reactor will be the same as the plug flow, what is the degree of conversion that is expected? Okay, so now in here, we're actually comparing the sizes of reactors and even their performance. How will they convert the reacting species into the product? Now we go to our solution. So we start with writing the performance equation for the plug flow reactor, because the original reactor where the reaction is to be facilitated is tubular, so it's plug flow. And this is the performance equation. Now for the tau, the space-time, on the left side of the equation, you have the volume of the plug flow reactor divided by the volumetric flow rate. And we have substituted values in here. And on the integral part, on the right side, we set aside CAO since it's a constant, and we write the differential of the conversion divided by the rate law in here. So we already replaced the negative R sub A by 500 C sub A, C sub B. So doing the maths, so you have 2 in here on the left side. You have here CAO, And since we know, as shown to you in here, that whenever the initial concentrations of the reactants are equal and the stoichiometric equation have the same coefficients for the said reactant, their concentrations after some time would be equal. So it was shown to you in here that for C sub B, if it's represented as C sub B O times 1 minus XB, and you distribute the C sub BO in here, you will have this. Now your C sub BO is C sub AO, and your C sub BO XB will be C sub AO XA as well, based on the stoichiometry. Then we conclude that your C sub B would just be equal to C sub A. So we go back to our rate law, the original rate law now, which is 500 C sub A, C sub B, is written as 500 C sub A squared. Now, since your integral has the unknown function x sub a, you have to translate or convert the c sub a here to c sub ao and xa in terms of these two. So we have expressed c sub a here in terms of c sub ao times the quantity 1 minus xa. It's squared, so we square also these two terms that are multiplied. We can cancel the CAO here, and we are still left with one CAO in here. So further simplifying the expression, you will have this on the left side. We transfer the 500 and the remaining CAO from in here. So you have this now to integrate. So if you integrate, this would be your corresponding answer after you have already substituted the limits. Your hour unknown in here is one of the limits, and that's the upper limit. So you get here a value for the conversion in the plug flow reactor, the conversion of which is 0.9091 or 90.91% of A is converted in a plug flow reactor of size. So the size of our plug flow reactor is 0.1 liter with this much volume being processed per minute. Okay, so this already answers letter A, the conversion in the plug flow reactor. Now for letter B, for this same conversion computed for the plug flow, what do you think would be the size of the mixed flow reactor needed to achieve the same degree of conversion? So of course, we need to write the performance equation for the mixed flow reactor. This time, it's not anymore in the form of an integral expression. Then we replace the volume of the plug flow by the volume of the mixed flow because this is our unknown. And you have here the volumetric flow rate. You have the CAO. This is the conversion. You have the 500. This is the CAO. We square. And this is 1 minus XA, which is also being squared. Now notice that for the same degree of conversion, in the mixed flow reactor, this much of volume you need. You need this much, or you need this big of a mixed flow reactor to achieve the same degree of conversion as in the plug flow reactor. Okay, so of course it's bigger, a lot bigger, because the plug flow reactor is just, as shown to you, the volume of the plug flow reactor is just 0.1. The mixed flow for the same conversion has this much of the volume. This is what you need, the volume that you need, okay, for the same degree of conversion. Now, what if in letter C, you are going to use a mixed flow reactor whose volume, or which has a volume equal to that of the plug flow? So it's asking, let's say you're going to use a mixed flow reactor as small as the plug flow, which is only 0.1 liter. What degree of conversion is expected? Okay, so since we're talking about the mixed flow now, your performance equation should be that of the mixed flow reactor. And you need to replace again the tau term here by V sub M over V sub O. And since V sub M, it should be replaced by V sub P. So this is the size now of your mixed flow reactor, which is equivalent to that of the plug flow. And you are to determine the corresponding conversion. So everything is just substitution to this particular formula. And you'll be having an expression which has x sub a as the unknown, quadratic in nature. So if you simplify that, this would be the corresponding answers that you'll be getting. You will have an x sub a, which is 0.73, and you have an x sub a, which is 1.37. So I place here this is not acceptable because we know that in terms of conversion, we don't have a degree of conversion which is exceeding 1. We don't even have 100% conversion. So this is the, in terms of validation, this is the acceptable value. The degree of conversion for a for a mixed flow reactor the same in size as the plug flow is 0.73, or that's 73%. So you can see in here from this particular sample problem that your plug flow reactor is more efficient than your mixed flow reactor. Though it's more efficient because the degree of conversion for the mixed flow here is just 73%, whereas for the letter A that we have determined for the plug flow of the same size as the mixed flow, you have 90.91%. So in all of the ideal reactors, actually, it's the plug flow reactor which is more efficient in terms of converting the reactant to the product. In terms of the volume that could be processed, of course, we have, or the volume requirement, we expect that the volume requirement for the mixed flow will be bigger. So that's the key points that you should be able to, shall I say, get from this particular sample problem, simple as it is, but that's the important learnings that should be extracted from doing the calculations related to this sample problem. Now, do you have any questions? Do you have any questions as to any part of the solution? There's none? Okay, so if there's none, we will continue with the next set of slides.